To understand game theory, we need some sense of where it might be applied successfully and where its applications may fail. The idea is supposed to be that game theory enables us to explain why things happen. And as an illustration of that, one of my favourite illustrations actually, I want to tell you about the side-botched lizards. So here are three males, and what you might see if you look carefully is that the three males here look rather different. They've got quite different patterning. And in fact, this one here is a highly aggressive male. So a male with this kind of patterning is basically always going to fight you if you're in competition with this male for a scarce resource. And typically that scarce resource will be the company of a female lizard. These are the males. So here you see two males here again. Now this one, yeah, I think I've got this right. This is the pacifist in the world of lizards. So this one, if you meet this one, it's not going to fight you. It's always going to back off. It's always going to back off. So if there's competition between you and this male for a female, this one will back off. And then thirdly, there's what these authors call a sneaker. So this is a male lizard which actually looks just like a female. It's sort of disguised itself as a female. It's got the female patternings, and it tries to sneak around in order to get the attentions of the female without coming into conflict with the aggressive lizards. Now, the question here is, look, why is it that we have these three kinds of patterning? How come, for example, the most aggressive kind doesn't simply dominate and become the only kind of side-botched lizard that there is? Why is it that there are these three different kinds in an evolutionary stable configuration? The proposal is that we can answer that by appeal to game theory, and in particular by relating the way that the lizards behave and are to a game that might be familiar to you as rock, paper, scissors. I hope you've played that. If you haven't played that, I'm sure you can find someone to play rock, paper, scissors with you. And when you've done that, come back here. Now here's the game represented in the standard game theoretic way of rock, paper, scissors. So for example, if we both choose rock, neither of us win. So that's a 0-0 situation. But if you choose rock and I choose paper, right, the paper wraps the rock. So there we go. I've won and you've lost, right? So that's a situation in which things go well for me, and so on. There are also kind of amusing variations of this game. So I think there's bunny, carrot, shotgun. Is that right? Something like. Good. Yeah, that's right. All right. But that's maybe a bit too rude for this course. So, but thank you for putting that thought in me while I'm trying to give a lecture. Very good. All right. Now, sorry. Totally inappropriate. Now, here's the thing about this game. I want you to tell me, where are the Nash equilibriums? Because one of the things we're doing, studying Nash equilibriums, you should be able to look at a variety of games and try to figure out where are the Nash equilibriums. So just take a moment here, perhaps 90 seconds, pause the video and tell me where are the Nash equilibria in this game. All right, so I'm going to suppose that you've had a good think now. And you've maybe noticed that I was offering you a trick. Yes, you did. I was offering you a trick question. Okay, I'm sorry if that was confusing. Look, there are no Nash equilibria in this game. So no matter where you are in the game, one of you can always profitably deviate in order to get a higher score, and unilaterally profitably deviate. So there are no Nash equilibria. And that's an important fact about this game, because it explains why rock, paper, scissors works as a game at all. Right? If one of these strategies, for example, was dominant, then it wouldn't be a very interesting game, because you would always pick the dominant strategy. Right? So noughts and crosses, for example, there's a dominant strategy for player one. So it turns out that it's not such an interesting game. It wouldn't be very useful if we wanted to use, so typically we use rock, paper, scissors in order to decide who has to do something unpleasant or costly. It wouldn't be very useful to use noughts and crosses. Why is that? Well, because in this case, there's no Nash equilibria that we have here, and therefore no dominant strategies either, whereas in noughts and crosses there is. So this is a useful fact about that game, and it explains certain aspects of human behaviour. But what these researchers have shown is that it also explains the evolutionary behaviour of the side-botched lizard. So what the researchers demonstrated at some length, if you read the paper, which is also cited on the handout below you, what they demonstrated is that the lizards are in effect taking different roles in the rock, paper, scissors game. This is the structure of their behaviour. So if the dominant one comes across the pacifist, then the dominant one has an advantage. So they win the game of rock, paper, scissors. However, the thing about being the dominant one is that you're disadvantaged relative to the sneaker, because as a dominant one, if you hit another dominant one, you have to have a fight, and that's pretty bad news, right? That's pretty costly. That's a cost that the sneaker never has to bear. So the sneaker beats the dominant. On the other hand, the pacifist beats the sneaker because the pacifist is kind of clearly identifying a male and going to have freer access to the females and so on than the sneaker. And of course the dominant one here beats the pacifist, because when the dominant threatens, the pacifist walks away and the dominant then gets what he wants for free. So why are there three kinds of male side-botched lizards which play these different roles? How is that a stable pattern? The answer is they're playing a game in which there's no Nash equilibrium. So that combination of strategies is stable. So this is interesting to me because it's a case where game theory seems to be successfully applied in explaining an aspect of behaviour. So if you're interested in studying game theory, and you needn't want to go into it terribly deeply for the purposes of this course, because we're actually going to go on and look at team reasoning and other things as well. But if you did want to follow up on this, then one of the first things you'd want to do is to find cases where game theory explains things that interest you. So you don't need a list from me, but I compiled one anyway to give you a sense of the sort of diversity of domains in which game theory or variants of it has been used. So we've got legal concerns to do with inequality, culture and power, for example. We've got a very nice explanation of why you get a tragedy of the commons effect. So in conflict over resources, often you and I and all of the others consume more of the resources than would be optimal for us collectively. So we could, if we wanted to, live in a world that was better for all of us, but we somehow fail to do that. And that allegedly can be explained through game theory and so on. The important thing to know here is, first of all, that if you're interested in a particular domain, you can probably find a case where game theory has been applied. And I would encourage you to do that. Don't use this list particularly. I'm not particularly recommending these sources. I'm recommending that you go away and find some sources that are interesting to you. And by the way, share them with me if you find something good. Thank you very much. Second thought is that applications of game theory have been successful in a wide range of domains. So while you might have some quibbles about some of these, maybe you're not totally convinced about my side-botched lizards, although I do think that's actually a pretty solid case. But you may have debates about certainly the tragedy of the commons explanation that Tadelis offers in that textbook. You may find that there's room for debate about that, for example. And the question about the foraging behaviours, the Hansen is studying the bald eagles, if I remember rightly. Of course, it could be that there's just some kind of empirical problems there. This was an empirical issue, and it could be there's some problems there. So I'm not saying that it's certain that all of these applications work. I'm saying that if you do even a fairly brief survey of applications of game theory, you will see that there are many cases in which game theory successfully explains behavioural phenomena. So game theory is supposed to describe rational behaviour in social interactions. That's the aim. What we've seen previously, looking at dominance and Nash equilibria, is that our basic form of game theory tells us that we should act by, first of all, avoiding actions that are dominated, and secondly, by selecting a non-Nash equilibrium. So this is a kind of an advice about what it is to act rationally, or sorry, I shouldn't say advice, it's a description of what it is to act rationally in a social situation where we're playing a non-cooperative. You remember that we can't force agreements between us, one-off game, it's one shot, so we'll never see each other again, we're strangers at the start. The question, of course, is, should we accept this? The many successful applications are an indication that we should, but as philosophers, we are going to want to go quite slowly here. So let's have a think. What follows from the idea that it's rational to avoid dominated actions? Well, one thing that follows, as we saw previously, is that in a prisoner's dilemma, you should always confess, or that's sometimes called defect. So you should always, in effect, try to create problems for the other person playing the game with you. And perhaps if you both confess, you'll come out with a sort of slightly okay outcome. Right? That's what you should do. And Dixit and colleagues say this is an explanation for why cutthroat competition in business occurs. It's because those rivals are engaged in a prisoner's dilemma. It would be best if the firms could jointly agree on high prices, but because we've got a non-cooperative game, anti-monopolies, their firms are unable to do that. The result is cutthroat competition, which is bad for both of the firms, right? Perhaps good for you. And Dixit and colleagues' thought is, look, the reason we get cutthroat competition is because we are playing a prisoner's dilemma. So here's a case where game theory's view about what's rational seems to have explanatory force. And actually, Dixit and colleagues mention many further situations involving birds, businesses, countries, and individual adults in which this same kind of reasoning appears to apply. So on the face of it, still, once again, the game theoretic explanation looks to be highly successful. But just step back and think for a moment. So you and I are playing a prisoner's game, we're complete strangers, we've never met each other before. What will we do? Well, if we follow the advice never to accept a dominated strategy, we cannot rationally both resist. Game theory says, look, rationally you cannot do this. What you have to do instead is this. But when humans are actually placed in this situation, so they're given a one-shot non-cooperative game with a complete stranger who they'll never meet again, they don't even necessarily know who they're playing with, what do? Sometimes they resist. And those who resist are sometimes going to get more than those who lose. So it's a kind of strange idea in a way that only this is a rational combination of actions, and anything else, including that combination of actions which gets both you and I a much higher reward, is somehow irrational. I'm not saying that's wrong, I'm saying that it's far from obvious that it's true. So here we've got two things. On the one side, we've got actual explanations, scientific explanations of behavioural phenomena which appeal to the game theoretic notion of rationality, and in particular the idea that it's never rational to choose a dominated strategy. That seems to be an idea that's incredibly useful on the one hand. And on the other hand, it's far from clear that we should accept this, that we should walk away from the potentially high reward and live in a world where you and I always get the worse outcome when there is a better one available. Is that rational? Hard to say. Hard to say. So I want to say here, look, there's a question about this. We shouldn't accept this uncritically. Not that I've given you an objection to accepting it. Clearly I haven't done that. Now, what about the second piece of advice? So the second piece of advice from game theory is, look, Nash equilibrium is Nash equilibrium. Select one and you're fine. You've met the criterion for rationality. We'll take a look at this game, which will be important to us later on the course when we come to team reasoning. So here's a game sometimes called the footballer's problem, sometimes called high-low. You can select to go high, and I can select to go high, in which case we both get a good outcome, our absolute preferred outcome. We can both select to go low, so we could both get a less preferred outcome, but still quite a good one. Or we can go different directions, and in that case, we'll both get nothing. We'll both get nothing. So you can imagine this as a situation where two footballers are unable to communicate or agree anything with each other. They have to decide in the moment between which of two strategies. They both have to decide on the same strategy. One of those strategies is perhaps, let's say, much more likely to score a goal, or will put the team in a better position than the other strategy. Now, the curious thing here is that there are actually not one but two Nash equilibria. So this is a Nash equilibrium. No player can unilaterally deviate and improve their outcome. But this is also a Nash equilibrium. Now this is kind of strange because most people, when they look at this problem initially, unfortunately you're not here for me to ask all of you, but most people will say, look, the obvious thing to do is to play high. the obvious thing to do is to play high. But from the point of view of standard decision theory, low is just as good. Rationally speaking, low is just as good. And in fact, there's no unique solution here. So sometimes you might play high and sometimes you might play low. And it wouldn't be irrational. Now this suggests, sorry, I should say we'll come back to this later when we come to see team reasoning. That's why I'm moving fairly quickly through the high-low point. What you need to know for now is just that there are these two Nash equilibrium. So if we think that an action is rational in a non-cooperative one-off game, if it's a member of a Nash equilibrium, then we're saying it's fine for you to choose low in that high-low game. Nothing wrong with you at all as far as rationality goes. Now, of course, that might be right. That might be the right attitude for us to take, but it's far from obvious that it should be. So once again, I don't say I've got a decisive objection, not at all, but it looks like there is a big question mark about whether this is really what rationality requires. So if we accept game theory as a description of rational behaviour in social interactions, we have the advantage that it's clear to us why game theory has so many successful applications, because it captures rationality in social interaction. But we also have to accept some consequences. We have to accept that both of us resisting and thereby getting a really great outcome in the prisoner's dilemma, that's not rational. But that choosing low in the high-low game is rational. Right? We have to accept that as well. And that seems a harsh consequence to bear. So if you're like me, you're a bit torn between two thoughts here. I'm really impressed by the cases where game theory is successful. So I'm moved to think that there is something to the idea that it's describing rational behaviour in social interaction successfully. On the other hand, the consequences to me do not seem tenable. It seems to me likely that we can generate substantial objections by reflection on one or both of these outcomes. More on that later. And that's pulling me away from the idea that I can think of game theory as a description of rational behaviour in social interactions. So gosh, what am I to do?